Hey there, welcome to the Electronics channel. I'd like to show you how to design a common emitter amplifier given a set of criteria for that amplifier. So this circuit right here is the common emitter amplifier, where I connect the input to the base and I have the output taken at the collector. When designing an amplifier, you'll have a set of criteria being the VCC value, perhaps, the gain that you need, the input and output impedances that you need. And basically what you're doing with that set of criteria is determining what values for RB1, RB2, RC, and RE you're going to need for that particular design. So the criteria for this particular amplifier that I am going to design are VCC, or my supply voltage, needs to be 24 volts. My open circuit voltage gain needs to be 100 or negative 100. This is an inverting amplifier. And I need to have my collector current at 4 milliamps for biasing. Now here's some useful design hints or rules of thumb to follow that will help you in the design of this amplifier. The first hint is I want to try to bias this to the middle of the load line. Now ideally I'd want to bias it to the middle of the AC load line, but in order to know the AC load line, I need to know what my load is that's going to be connected to Vout. In this particular case, I don't know what that is. So I'm going to bias to close to the middle of the DC load line, and that should work for my situation. If it doesn't work, then I just have to do a redesign. So biasing to the middle of the load line means that I want to set it up so that my collector emitter voltage is about 12 volts, and my IC sat, or the saturation current, is 8 milliamps. So this 12 volts comes from being half of VCC, and this 8 milliamps comes from the requirement that my operating point for my collector current needs to be 4 milliamps. So if that was to be in the middle of the DC load line, then my saturation current needs to be at 8 milliamps. Also, to allow me to make the approximation that no current is flowing into the base, I need to make sure that the resistance seen looking into the base is much bigger than this RB2 value. So in order for that to be true, then RB2 needs to be less than or equal to beta times RE, which is the resistance looking into this base, divided by 10. So with this set of design requirements and these hints that will help me in the design, let's go through the process of figuring out what resistor values I need. So first of all, I am designing it to have a collector current of 4 milliamps. That means right away I can figure out what my little RE value is. 26 millivolts over IE, and IE and IC are approximately the same. Okay, so now I know what my little RE value is, so the internal resistance between the emitter of the transistor. Number two, I can figure out what RC value I'm going to need right away now too, because I know what my open circuit voltage gain is supposed to be. And I know the equation for calculating that for this common emitter amplifier. It's negative RC over little RE. Well, really over whatever resistance is in the emitter. And in this case, my big RE is bypassed by this capacitor. So from an AC point of view, that is a short. This is equal to negative 100, or I want it to be equal to negative 100. I know what value I have for my little RE, so I can figure out what RC value I need. Okay, third, I want to bias this circuit in the middle of the load line, in the middle of the DC load line, so I can look at what my saturation current is going to be. Well, I want my saturation current to be about 8 milliamps. And the equation for the saturation current will be the voltage that is across this RC and RE when I'm in saturation. So that's going to be 24 volts minus the collector emitter voltage at saturation, which let's say is about 0.2. Typical value for like a 2N3904 transistor, divided by RC plus RE. Well, I've just figured out what my RC value is, so the only thing I don't know in this equation is my RE value. So I can rearrange that equation to determine that RE is equal to 2,325 ohms. Now step number 4, I can figure out the upper limit for my RB2. RB2 has to be less than or equal to beta RE over 10. So again, this is a 3904 transistor. Let's assume that it has a beta value that ranges. So for this inequality, we'll have to assume that our beta is going to be the smallest possible. So I want RB2 to be less than or equal to 100 times RE divided by 10. And that works out to 23,250 ohms. So let's just pick a value that's something less than that. So let's go with RB2 of 20 kilo ohms. Step 5, this is the last step for a calculation of the resistors, is to figure out the RB1 value. I know the other 3 resistors already. There's a few steps in calculating RB1 actually. What I need to do is figure out what the voltage is across RB2, which is the base voltage, and then seeing this resistor network as a voltage divider of this VCC. Some of the voltage gets dropped across RB1, the rest across RB2. If I know this voltage and I know VCC, then I can figure out what voltage and what resistance I will need here. So the first step in that, calculate the emitter voltage. That will simply be the 4 milliamps I have for IC times my RE value of 2.325 kilo ohms. That is equal to 9.3 volts. Since VB is simply the diode drop more than VE, 0.7 volts more than the 9.3, so VB will be 10 volts. That's the same as the voltage across RB2. If I have 10 volts here, I'm going to have 14 volts here to get my VCC of 24 volts. So the voltage across RB1 is 14 volts. The 24 volts gets split as 14 and 10, so that ratio of 14 to 10 for voltage has to be the same ratio for the resistance of RB1 to RB2. That ratio is 14 to 10. Rearranging that equation, I get RB1 is equal to 1.4 times RB2. I've picked RB2 of 20 kilo ohms. So that means my RB1 needs to be equal to 28 kilo ohms. So I know all of the resistor values I need now for this circuit. RB1 is 28 kilo ohms. RB2 is 20 kilo ohms. RC is 650 ohms. And RE is 2,325 ohms. And that's it for the design of the circuit. I didn't have any specifications for the input impedance and the output impedance for this particular circuit, but let's figure out what those are and then apply an input voltage and a load and see what the actual overall gain is for that particular circuit given this open circuit. Okay, so I know that my open circuit voltage gain of this is minus 100. My input impedance is the impedance seen looking into the input here. And that's going to be RB1 in parallel to RB2 in parallel to the impedance seen looking into the base of the transistor. So that'll be 28 kilo ohms in parallel with 20 kilo ohms in parallel with beta plus 1 times little re. Remember the AC model, that RE resistance is bypassed by this capacitor. So let's assume again that the beta is 100, so we're going 101 times the 6.5 ohms of the little RE, and that works out to 4.17 kilo ohms. The output impedance of a common emitter amplifier is simply the RC value, so it's 650 ohms. So what this gives me, if I was translating this amplifier into a general amplifier model, I'll have an input impedance of 4.17 kilo ohms. I have an open circuit voltage gain here of 100 times V in. Connected to an output impedance of 650 ohms. So that's the general amplifier model of my common emitter amplifier that I've just designed. Now let's say I connect a voltage source that has its own output impedance of 50 ohms. And the magnitude of this input, let's say it's a 10 millivolt peak input. And then I've got a load connected over here, and let's say this load is a 1 kilo ohm load. So what is my output given this input to the amplifier that I've just designed? Well, I'm going to need to take into account the input impedance, the output impedance, and the voltage dividers that occur at the input and the voltage divider that occurs at the output. So what I will have is this 10 millivolts that gets divided between these two resistors. So luckily my input impedance is pretty high compared to the output impedance of the source. So that term there would be the input voltage. That gets multiplied by the gain, minus 100. And then that that's coming out of my dependent voltage source here gets split between those two resistors, with the output being across the 1 kilo ohm resistor. 1000 over 1650. When I multiply all of those together, it works out to negative 599 millivolts. So I apply this 10 millivolt peak signal in, and I get a negative 599 millivolt peak signal out. And what this represents, this is a 10 millivolt sine wave. This is a 599 millivolt sine wave that is 180 degrees out of phase with the input, as you would expect with a common emitter amplifier. So I hope that helps you if you ever need to design a common emitter amplifier with some simple design criteria. Thanks for watching, and I will see you in the next video.